from the top? Anyone not have it? Hands up. Okay. We're going to go through just some of those homework questions. So we're trying to finish on IP addressing. You know how to convert, or you should know now how to convert the different notations. That is, from the binary notation, the 32-bit binary number, to a dotted decimal notation. You have to know how to do that. I cannot help you anymore. I think that the concept is basic. And the other thing you need to know is that a computer has an IP address. In fact, more specifically, an interface, like my wireless LAN interface or a router interface, has an IP address. But it also has a subnet mask associated with it, another 32-bit value, which tells us for that IP address which bits in the IP address identify the subnet I'm in, and which bits in that IP address identify the device in that subnet. So it's some hierarchical addressing. And the subnet mask is read by, or is a sequence of bits which tells us which bits in the IP address correspond to the network portion and which bits correspond to what we call the host portion. Swap your homework with someone else. They're going to mark it for you. Exchange quickly. Make sure your name is on there. Do you have any answers? Make sure your name's on the top and swap. Make sure you don't have your own. And we will not go through all the answers. We'll just go through some examples. The answers are on the website. I'll point to them in a moment. First quick one. So here was in practice of converting IP addresses to dotted decimal notation to binary, and looking at subnet mask, network addresses, broadcast addresses. Let's consider this one, for example. Okay, we'll just go through one of these quickly. What we're given is the IP address, say, of a computer. My computer has IP address 140.168.32.21, and it also has a subnet mask, 255.248.0.0, and I've written them on the board. We can express a subnet mask in three ways, three different notations. The dotted decimal notation, like in the question, binary notation, just the 32-bit value, and let's write that quickly. 255 we know is simply 8 ones. 248 is how many ones? Or what is the value in binary? How many ones? 5. 1, 2, 3, 4, 5, followed by 3 zeros. You can check that conversion. It's 248 in binary. And 0, 0. That's our subnet mask, the binary form, the real value. And the third notation we have for a subnet mask is this slash notation, because the subnet mask, from what we deal with, is always a sequence of ones followed by a sequence of zeros. How many ones? 13. So the third notation we use is this, what we call slash notation, slash 13, meaning our subnet mask has 13 ones followed by 19 zeros, because we have 32 bits. There's your answer there, slash 13. The binary form for the IP address, I've calculated before to save some time. 10001100, and 21 is 00010101. Our IP address and our subnet mask. The simplest way to answer these questions is always convert back to the binary form. and deal in binary form. Of course, it takes some time to do the conversion, but it demonstrates the concepts the easiest. The next question asks, what is the network address? The network address is a special address that identifies a subnet in the internet. Remember, our internet is made up of multiple subnets. A network address is that we take the network portion of the IP address and set the host portion to all zeros. Before we go on, Anne is going to do the evaluations. Do the evaluations in 5 or 10 minutes, and then we'll continue and go through that example and the other homework examples. when you've finished, you can look at some of the answers. Mark your friend's answers in the question. Let's go through and see how we find the number of hosts. These answers are on the website, so I think you need to find them from 2010. If you find the ITS323 for 2010, you can somewhere find this question, the question sheet, and you'll also find the answers to check. Let's go through this one. Let's arrive at these answers where we've started here. We know the subnet mask has 13 ones. That tells us for our IP address, the first 13 bits identify the network portion of the address, and the last 19 bits, therefore, are the host portion. There's a special network address which identifies a subnet in that internet. This subnet is identified by the first 13 bits. So if we take them, and for the network address, take those first 13 bits and then set the remaining bits to all zeros, 19 zeros, then that's our special network address. It's an identifier we can use to refer to a particular network or subnet. And if you convert back to dotted decimal, of course you'll still get 140. This will be 16, and then we'll have 0, 0. 140, 16, 0.0 is the network address. Your computer cannot have such an address. It's wrong to assign a network address to a particular interface, a computer. It's reserved to refer to an entire network. Okay? So you cannot use that to assign to a computer interface. There's another special address called the directed broadcast address. It's used to send to everyone on that network or subnet. We can calculate it in the same way, except instead of setting all these bits to 0 in the network address, set them all to 1. And we get our broadcast address in binary, BC broadcast, which converted back to dotted decimal will still be 140, and now we have what? What's this? 7, 23. 16 plus 7, 23. 255, 255. That's our directed broadcast address. So we can think every subnet in the internet has these two special addresses. One to identify that network in the internet, the network address, and another that can be used to send to everyone on that network, the directed broadcast address. Neither of them can be used to be assigned to interfaces on computers on that network. The remaining one is how many hosts, in fact, hosts is maybe the bad word there, how many interfaces can we assign unique IP addresses to? In this subnet, every device must have the same first 13 bits. Therefore, we have 19 bits that we can vary. The remaining, the host portion, we have 19 bits. So computer 1 or interface 1, the first 13 bits are the same, this 13 bits, and the last 19 bits can be any value except two special cases. They cannot be the case of all zeros, the network address, that's reserved for network addresses, and they cannot be the case of all ones. So we have 19 bits, one of those is 19 zeros. We cannot assign that to a host interface. And another one is 19 ones, and we cannot use that for a host interface. But any other value we can use. So you could list them. And I'm not going to attempt. And you list them all. There are two values you cannot use, all zeros and all ones. So that means with 19 bits, there are 2 to the power of 19 possible values, minus these two red ones, the two values we're not allowed to use. And that's, in theory, the number of IP addresses we can assign to hosts or to interfaces in that subnet. 524,286. And that's the same in all those other variations of the question. So we have a range of addresses that we can assign to computers in our subnet. In this case, we have 19-bit values. We can use any combination of 19 bits except those two special ones, all zeros and all ones. Does that clear? Okay. Any questions on this question 4? We're not going to go through any others unless you have questions.
If
Yep.
address is reserved for private network, which is
All right. We haven't covered everything about IP addressing. What we've covered, and in fact the only thing we'll cover in this course, is some very basics. In real life it's more complex than what we cover. There are some other addresses which are reserved for special purposes, like the addresses for private networks. Some addresses listed here should be used just inside an organisation. They do not correspond to public IP addresses. You've seen some of them when you set up your own network at home or on your computer, 192.168.1.1 and similar addresses. You see them in SIT, 10.10.6.1 and so on. These are what we refer to as private addresses. They are specific to... We have a visitor. Okay. They are specific only for inside an organisation, and it means they cannot be reached if you're outside of that organisation. They may affect the number of devices. That has an impact on the number of hosts that we have. That is, that we cannot use all possible addresses in some cases. We're not going to cover why we need them. You cover them next semester in computer network architectures and protocols. You look at, okay, in reality, there's some problems with the number of addresses we have. And there are some solutions to address those problems. And we see things like network address translation. But we will not go into that detail in this course. It needs another topic or two to explain it. You may see it in the lab next semester as well. For this course, just take the simpler approach that we have. All addresses are public IP addresses. Another thing that we will not cover again in this semester, but you will next semester, is how do we assign these addresses? Who gives you an IP address? When you turn on your laptop, do you need to type in your own IP address? Anyone? Normally you do not. When you connect to SIT's network, you do not type in your IP address. You could. In Windows, there's the properties, you can set your IP address. But normally you don't do that. There are some ways to automatically assign IP addresses, DHCP. We will not cover how that works this semester. You will do it in the lab next semester. And also, there's ways or there's procedures for how the subnet masks are assigned to different organisations. I think on the last slide there's a few notes on that. How do you get an IP address? Well, there's an organisation, IANA, that manages the assignment of IP addresses. In fact, they distribute amongst regions. So in the Asia Pacific, there's an organisation that assigns a subset of those IP addresses to different countries. And inside Thailand, there's THNIC, Thailand Network Information Centre. They have an office at NECTEC at Science Park at Rangsit. They are responsible for assigning ranges of IP addresses to different organisations. So what you do if you start your own company and you want to have your own subnet, you go to one of these organisations and they assign you a network portion with a subnet mask. So they may assign you this 13 bits and the subnet mask /13. Then it's your responsibility to give your hosts appropriate values of the host portion. That's up to you as the network administrator to assign hosts, and you need to assign them uniquely. So the ways to do that and the procedures, that's a summary, but in practice it's more complex than what we have time to cover. How that assignment happens. Any questions on this part of the homework? Glad you could make it to my lecture. That's good. You're welcome to come back after at the IT section as well, so you get the double intake. Let's move on to one of the later questions in the homework. And it's about arriving at the routing tables. And it involves multiple steps. So what I've given you here is an internet. How many subnets? Hey, someone said a number. Someone said a different number. 4, 6, no. How many subnets in this internet? 6, no. 4, no. 2, no. 8, no. No. More. How many subnets? Now, all right, you have to read the explanation, but you've done this. We have hosts, these H's, H1 up to H6. We have routers, A, B, C, D, E, F. Remember, routers connect subnets together. So in this question, we have a subnet here. We have the host is attached to one. Imagine there's a cloud here or a circle here. This is one subnet. And this router connects to two other subnets, to router A and router D. So here's two more subnets. Another one here. These are separate subnets in this example. This is one subnet. No, this is a switch. It's not a router. That's at the lower layers. For example, a Ethernet switch, or maybe it's a wireless LAN access point. That's not involved in the IP forwarding. So from our perspective of subnets, this is one subnet with one router and two hosts. And same here. So these are routers, and routers connect subnets together. In this example, there are 11 subnets. 1, 2, 3, 4, which hosts are attached to, and then 5, 6, 7, 8, 9, 10, 11 subnets in this case. And what's shown is that each router has connections to multiple subnets. So router C has 1, 2, 3 connections, connects to 3 different subnets. And I've labelled the interfaces, C1, C2, C3. Your first task was give IP addresses to those interfaces. So I use interface labels just to keep things short. But in reality, each interface has an IP address and subnet mask. For example, the 6 hosts, which have a single interface, H1 through to H6, I've given some information about IP addresses. And also for the routers in the next table. Router A, I've given some information about the interface, the IP addresses for 3 of its interfaces and missing some for interface 4. Let's just do one example. Let's find the IP address or select an IP address for host 1. Host 1 is on a subnet connected to router A, in particular connected to interface A1. Okay, so if we drew that, we have H1 and then a router, and here's A1. Find the IP address for H1. If you haven't done it, have a quick attempt. Find the IP address for H1. And looking around, not many people have found it. Some. How to find it, that's the challenge. And the hint comes from what I've drawn on the board. This is H1 here and this is A1. They're on the same subnet. What does that mean? Two interfaces on the same subnet. What does that mean about their IP addresses? That
the network portion should be the same.
The network portion for both of those addresses should be the same. Remember, the network portion, say the first X bits, identifies what subnet we're on. 2 computers on the same subnet must have the same network portion and must have a unique or a different host portion. So, we want to find the IP address for H1. Here's the hint. The IP address for A1 is given. 60.45.12.3/28. The IP address for H1 must have the same subnet mask, and the first 28 bits for the IP address for H1 must be the same as the first 28 bits for A1. And the last 4 bits must be different. What are the first 28 bits? So what you would do is convert that dotted decimal notation address into binary, take the first 28 bits and copy them, and the remaining 4 bits, if you look, I think you'll find the remaining 4 bits, the last 4 bits, because it goes up to 32, 3 in binary, in 4-bit value, 0011. The first 28 bits are some values. We copy them to here and change the last 4 bits, for example, to be 2. Because I think if you check through, 2 is not used by any other devices. Or in binary 0010. This is the host portion. And then you copy the 28 bits from here. And if you do so, if you copy the first 8 bits, you'll get the same decimal value. And the next 8 bits, you'll get the same decimal value, 45. And the next 8 bits, you'll get 12. And then in this case, we'll end up with 0010. The first 4 bits will be 0, 2 in this case. So here is a IP address for H1. The value you select here can be different. It didn't have to be 2. It could have been 1. It could have been 5. As long as it's a value where the first 4 bits are 0 and the remaining 4 bits are different from 0011. That is different from A1. Okay. So the rule there is that devices on the same subnet must have the same network portion of the address. And they must have a different host portion. Given that, you can find the IP or a IP address for H1. You apply the same approach for all the other IP addresses.
What about H2 because A4 is not given?
In some cases, there's not enough information given to give you the precise value, in which case you choose a value. That is, I think you find for H2, H3 and A4, in the given information, H2 finishes 13.1, 14.1, H3, and A4 finishes with 12.1, and we have a subnet mask. You need to choose the first 2 dotted decimal digits. Yeah. It turns out you can choose any value, except you cannot choose values which are used in other subnets. Okay? So in this question, there are multiple different answers which are correct. You get to choose the values here. But you cannot choose the same values as used by other subnets. You could not choose, I think in this case, 130.20, because that's used in another subnet. You have to be careful then. So in this question, there are multiple correct answers. You just need to follow the rules. All subnets have a different network portion. All hosts have the same network portion if they're in the same subnet, but a different host portion. So that's then a task of applying those same rules for all the other values. Try it for, which one? Try it for H4, host 4. So try it for H4 and see what you get. Find the IP address for host 4. So consider what other devices are on the same subnet. Okay, so people are on the right track. H4 is on the same subnet as C3. Therefore, the two IP addresses for C3 and H4 must have the same network portion. So you need to then check, is there an IP address for C3? And yes, there is. The IP address for C3 is 190.551/24. Convert this to binary, take the first 24 bits, and they must be the first 24 bits in H4 address. And the last 8 bits you can choose as long as you don't choose the same as C3. What do you get? What's the address for H4? H4 190.5.5.2. Okay. C3 is 190.5.5.1, and with H4 you must have 190.5.5. something, and in the table it gives you a .2. And here's where you see some shortcuts that you can apply in the IP addresses. The rule or the approach is you take the dotted decimal notation, convert to binary. If you always do that, you'll be okay with the subnet mask, and then take the first X bits. But with some subnet masks, it's even quicker if you can avoid the conversion to binary by just looking at the dotted decimal notation. If it's a subnet mask of /24, it means the first 24 bits are the network portion. In the dotted decimal notation, the first 24 bits correspond to the first 3 decimal numbers. 8 bits, 8 bits, 8 bits. So if it's /24, we know that every other device on the same subnet must start with, in decimal, 190.5.5, because that corresponds to the first 24 bits. Okay? So in fact, you can do a shortcut calculation and not convert to binary. The same if it's a subnet mask of /16. /16 means the first 16 bits, which corresponds to the first 2 decimal numbers. 8 bits plus 8 bits. So at the middle dot. So on B1, any other device on the same subnet must start with 130.10. And the remaining 2 dotted decimal values must be different. And /8, the first bit, or the first dotted decimal number. Only use that to speed up your calculations. If you do not understand how to use that, then just convert to binary always. But if you can understand that point, then you can save time in the conversions. If you don't understand that point, I suggest just convert to binary, and then you'll start to learn the shortcuts. You go through and fill out all those values. And you get, they may not be the same as what's on the screen here, because some cases you can choose your own value, but you get some IP addresses for all the interfaces in the network. The next question was calculate the least cost paths. You can do that manually, or you can use software. I've done it, I can't remember how I did it this time. I think just manually. Find the least cost paths from every subnet to every other subnet. That's what they are. Where to go from subnet or router B to router A, the path is B to A. The cost is 3. To go from C to E, the least cost path is CABE. And the cost is 9. You have to go through and do them manually. I would not ask in the exam to do such a large calculation. Maybe a small network with a few nodes, but not one that's so time consuming. The important part is, given this, given the least cost paths, create the routing tables, which is the last part. Find the routes, route discovery, and then use that information to create the routing tables. What's the routing table for host H2? And I give you the hints in the table for the host at least. For H2, remember the routing table stores the next node in the path. I've given the interface label, you should give the IP address. The next node, the next router. For host 1, the routing table is to reach any destination. The star means any value. To reach anyone on the internet, send to the next router identified by label A1, which has the IP address, and that's what we calculated in the previous step, of 60.45.12.3. That was the one here, /28. Then do the same for H2 through to H6. What is it for H2? Actually, H2 is a bad example because you may choose different values. What about... No. I've given you H4 as well. H5. Try H5. Because there should be just one answer then. What is the next router for H5? And in fact, I give you the hint. It's the IP address for the interface F2. Why? If we go up to our network, each of the hosts are attached to just a single subnet and a single router. So from H5 to reach anyone, they must send to F2. For H6 to send to anyone, they must send to F2. So that's why we have a very simple routing table for the hosts. We say for any destination, the star value, the next router for H5 and H6 will be send to F2. And similar for the other hosts. For H3, the next router will be A4. Because there's only one choice. So therefore, it's always must go to that router. If we had two routers we're attached to, then it would be more complex. But most cases, a host is attached to just a single router or a single subnet. Because of we're short on time, I will not calculate the IP address for F2. I've calculated it before. Sorry, I'll go back to the answers. When I calculated the IP address for F2, I got 200.10.5.1/24. It may be possible there's a different value, but I think that's the only one in this example. Yeah, /24. Therefore, the routing table for H5 is shown here. Routing table for H5 down the bottom. To reach any destination, send to the next router interface F2 200.10.5.1/24. Okay. Routing tables for hosts are generally simple. They can be more complex, but in most cases you just need one or several entries, because there's just one path to take. The routing tables for the routers are more complex. Let's find them. let's go to the more complex case and find the routing table for a router. I'll go back to the questions. We know the routes. I'll show them in a moment. Routing tables for routers. First, write down the network addresses. And I've done it for network 4. The network address, remember, we take the host portion and set it to all zeros. And we get the network address. So write down the network address for networks 1, 2 and 3. And network 1 is the one that has host 1 attached. Network 2 has host 2 and 3, and network 3 has host 4 attached. Write down those network addresses. Sorry. What is the network address for network 1? They are the IP addresses for the hosts. What's the network address for network 1? There's no need to copy the answers into the piece of paper from the website. It gives you practice in writing, but you got that in primary school. Other than that, it won't help you. You can look at the answers, that's fine. I will be not looking at your answers. I just want to know who's done it. So you write your own notes. If you don't have answers in your sheet, that will not bother me. It will not affect your mark. Find the network address for network 1. Some people have it. The network address for network 1. In your handout, it is in section 2.4. That's the question. Then remember the network address, you take the network portion for the IP address and set the host portion to all binary zeros. All binary zeros. Network 1 is the one with host 1 attached to it. This is network or subnet 1. Net 1 here. So net 1 is just a simple name I give to it, but in reality it has an IP address to identify it. We simply take here are the IP addresses for the hosts on that subnet. We take the network portion, which is the first 28 bits, which is somewhere up to here. So the first 8 bits, the next 8 bits, and the third 8 bits, and then 4 bits from the end. That is 28 bits. And set the remaining 4 bits to all zeros. What do you get? Anyone have an answer? 60.45.12.0. Easy. So the network address for net 1, 60.45.12.0. Include the subnet mask just to be complete. That's a special identifier for this entire subnet. And that's used in the routing tables. Because in the routing tables we say, what is the path to reach a particular network? Not what is the path to reach a host, But what is a path to reach all hosts on a particular network? So we normally use network addresses in routing tables. So that's network 1. You can also do it for network 2 and network 3. And so that we can finish in this next 10 minutes, the answers are given here. Network 1, 60.45.12.0. Network 2, which contains hosts 2 and 3. You can check from the IP addresses, at least in my case, 70.2.12.0. And network 3, which was our 190.5.5, and network 4. We will use them in the routing tables in the next part. We'll come back to that. Back to our diagram. Focus on router A. It's attached to 4 subnets, 1, 2, 3, 4. And in this example, in this question, we want to know what are the paths to reach the subnets with hosts. So this is network 1, 2, 3, and 4. The question is, what are the paths to reach those networks? To reach network 1, 2, 3, and 4. If router A has a packet and the destination is on network 1, where will it send it? If router A has an IP datagram, the destination address is one of those on network 1, where will it send it? Will it send to another router? Will router A send to another router? If router A has an IP datagram, and it's destined to someone on network 1, network 1 is the network with H1 in it. Does that router need to send to another router? No. We can say it can send direct to the destination. Someone sends a datagram. It's coming through the internet. It arrives here. Destination is, say, H1. We don't send to another router. We send to the host. So we can say in short term that, or shorthand to say, we send direct to the destination. So to reach anyone on network 1, I'm going to send direct. I'll just write direct. There are other ways to formally write that in a routing table, but the concept is we don't need to send to another router. We can send direct to the host. Similar, anyone on network 2, because router A is directly attached to that subnet, it doesn't have to send to another router, it can send direct to one of those hosts. But what about the other 2 networks, 3 and 4? If this router has an IP datagram and it's destined to someone on subnet 3, it cannot send direct. It will have to send to another router, either B1 or C1. Similar, to reach this network, if router A has the IP datagram, it will have to send to either B1 or C1. And which one Well, that's what we calculated when we found the least cost paths. We didn't do it today, but the answers, I'll just show you. It's in this table. If router A wants to reach a particular subnet, and in our case, from memory, the subnet attached to router C, we send direct to C. If we want to reach a subnet attached to D, we send to B. If we want to reach a subnet attached to E, we send to B. The next node in the path is B. And to F, we send to B. So, if A wants to reach a subnet attached to C, it will send direct to C. If it wants to reach a subnet attached to F, it will send to B. So in the routing table for router A, if we want to reach network 1, send direct. Do not send to another router. If we want to reach network 2, also send direct. If we want to reach network 3, which is this one with host 4 attached, we'll send to C. In particular, C interface C1. And if we want to reach the last network, network 4 with hosts 5 and 6 attached, from the routing least cost routes, we'd send to router B, interface B1. Want to get to here, send this direction. Anywhere else, send to B1. And then that will send on, and then that will send on to the destination. Here's our routing table for a particular router, A. These are the destinations. These are the next routers in the path. In this case, there are no next routers. We send direct. Here we have next routers. And then you simply, instead of used net 1, net 2, C1, B1, you use the real IP addresses that we calculated before, which is shown here. Instead of net 1, we say to reach anyone on network 60.45.12.0/28, send direct. To reach any host on the subnet 190.5.5.0, send to 130.20.0.2. Okay, so here we've used the network addresses. Here's our network address. So the destination is often not a host, but an entire network. The next router is either direct or another router address. And that's the real routing table for A, or at least in this example. Exam in 2 weeks, less than 2 weeks. Always questions about filling the routing table for a network. Any questions for today on how you would create the routing table for B?
Why this is 0?
The question is why are these values in the network address as 0? Because that's our definition of a network address. A network address is a special address. The network portion, we have the sequence of bits, and the host portion, all binary zeros. So we knew that the network portion was 60.45.12. It was a bit more complex. In binary, we have to convert it. And we set the last 4 bits to 0, the host portion. Convert back to dotted decimal and you'll get 60.45.12.0. Okay? So this is one of our special addresses, the network address. All host bits are 0. Any other questions? So again, to summarise the approach to fill in these routing tables, for each router, and I give you the hints to keep it short, for each router, find the path to reach one of those 4 networks. This is back to the questions which you have in front of you. For router B, if the destination is network 1, 2, 3 or 4, what is the next router for each of those destination networks? All right, it's easy to fill in these values because you've calculated them for just above. It's the network address. What is the next router? You need to know the least cost paths. So that's where you need to calculate those least cost paths, the route discovery. And then you simply find the next router in the least cost path and find its IP address, and that will be the routing table. The routing table normally does not contain net 1, net 2, net 3, D1. I've just given them for simplicity. The routing table contains the IP addresses. That's the thing that you're trying to find. So a real routing table will contain this value and this value. It will not contain a label like net 4 or D1. That's just so that we can match it back to the diagram. Any other questions on constructing the routing tables? Again, this is best learnt by practicing, completing these, not by copying down the answers, but by trying them. If you get it wrong, then you'll go back and fix it or check. Yep.
How do you know that which one is net 1, net 2, 3 and 4?
How do we know which one is net 1, 2 and 3 and 4? Somewhere in the question I give you that. Here. Network 1 is the network with H1 attached to it. Okay, so that's given in this case. Maybe on the picture in an exam I would draw and say this is network 1. It's just a label so we can easily refer to that network. The real label is the network address. Try these. Definitely try to complete these before the exam. There should be similar questions in the exam, the final exam. The answers for these are on the website. I think you can find them if you go back to 2010. Somewhere from the 2010 version of this course, you'll find the handout and also find the answers, so you can check what you've done. But try them before you look at the answers. Tomorrow we're going to move on to the second to last topic. We've got tomorrow to cover TCP and one lecture next week to cover TCP. The last topic is quite easy, it's HTTP. You did that in your assignment. We only need 30 minutes to cover that. So tomorrow and next week we'll cover some basics of TCP and then finish with something about HTTP, and then we're done.